Okay, good morning, everyone. Speaking about disease spreading last week, I've managed to catch one. So I apologize in advance if today is not going to be the best performance ever. But fortunately, the lecture is somehow easy to follow. So there is not going to be too much, hand waving and stuff. All right, so this is the 10th lecture. No, what? No, this is the 8th lecture. It's the 10th of November. Yeah. Question to you. What did we do so far? Let's say last lecture. What did we do in last lecture? Does anybody remember? Modeling, yeah, I mean, we've been modeling already 3 lectures back. We've been modeling disease spreading. That's why I got one. We looked at technology adoption, the S-curves. And we tried to model the technology adoption, and we used this famous model of disease spreading. Susceptible, the SIR framework, susceptible, infected, and recovered. I have to move here. This idea of modeling technology adoption is basically applied to market growth and to any kind of product or anything that penetrates a market, for instance. We also looked at the inventory model. This was 2 lectures ago. And for all these models, we investigated how small changes in whatever parameters, we talked about control parameters, what they could be, and how these small parameters can influence the dynamics. But today, we're going to be to introduce more formally what we mean by varying a parameter and observing a change. So far, we did it kind of heuristically, right? We change a parameter, and you see in Vensim, okay, some amplitude increases. Or 2 things become suddenly uncorrelated. But today we're going to be looking kind of mathematically what happens when you vary control parameters on the system's behavior. We'll define exactly what system's behavior is. And this is going to be also an introduction to chaos. So before we go on, can I ask you, what is your opinion? What do you think chaos is? It's not a question which has a right or wrong answer. I just want to get an idea what you think right now. What is chaos?
Behavior that cannot be predicted easily with linear modeling.
This is kind of close. Can you put some time frames? Like cannot be predicted, and we need a time frame here. In the short term, in the long term, never.
Behavior in the long term cannot be predicted based on the
Okay, yes.
behavior in a specific time.
This is one of the components. It's a necessary but not sufficient component of chaos, but it's true. So we'll look at chaos, what exactly it is. There is a strict definition kind of what chaos is from a mathematical point of view. It's not the same as you see in popular books or movies, butterfly effect and stuff like that. All right, so let's get down to it. Role of control parameters. I will introduce a few basic notions first about what is a dynamical system and what kind of things we're interested in a dynamical system. What we're interested in is this, basically. This is the equation that governs the evolution of a dynamical system. I mean, why is it called dynamical in the first place? Right? I mean, because we're interested in its dynamics, in its rate of change. This is the first derivative, basically. How it changes over time. And we assume, for all the systems that we saw so far, we assume that the way that the system changes over time depends in some nonlinear way on its current state and some control parameter. Now this is our control parameter. Of course, I mean this could be a vector of control parameters. It doesn't have to be one. It could be many. But things get more complicated, especially if you try to plot the phase space of a system with, I mean, 3 control parameters. You can't do it. You need 4-dimensional picture. All right, and when you have a figure like this, right? So this is the current state of the system, and that is the way that the system changes. And let's say this is the nonlinear function. All right. What are the points of interest? If you look at this figure, what are the points of interest? For nonlinear dynamics, the points of interest are the points where the system is stationary, so it doesn't change anymore. When would the system stop changing? Well, obviously when the first derivative is 0, when its rate of change is 0. So this point here, this point here, and this point here. These points are called stationary points. ST, this here. It's not stable, it's stationary. Or it's also called equilibrium points. Mind you, we make no statements about the stability of these equilibrium points. We'll investigate how to find that out. But for now, these are equilibrium points. And the number of equilibrium points and their stability depend on the control parameter. Okay? So you can immediately see where we're getting to. By varying the control parameter, u, in this case, or vector of control parameters, we expect something to change with these equilibrium points. And this is the change in the system that we observe, the system behavior that I talked about. Right? Something is going to happen to these equilibrium points. Before that, let me give you a few notions of stability. Even without introducing any mathematical treatment for finding stability, let's look at this point here. If we're at that point, the system is static. It doesn't change anymore. But imagine there is a little shock to our system. So, random shock. And suddenly, we jump here. Whoa. We jump right here, okay? What happens then? What would happen in the next few time periods? We're here, which means that the rate of change is negative, right? This is below the 0, which means that x, so x here, would decrease in the next time period, right? So we will be kind of pushed here, but because of this dynamics, we'll go back to our original position at 0. The same thing, if we're pushed up there, the rate of change is positive, which means that x, your state variable x, would increase in the next time period. So we'll be pushed again back to 0. So even by looking at the way that the nonlinear function f crosses the x-axis, you can kind of intuitively guess whether the point is stable or not. And this is actually how stability is defined. Small random shocks die out. They don't get amplified, they die out. And this is what happens here. We'll go back here. And as an exercise for you, even now, you can apply the same logic to that point. Not to that point, because we don't know what happens here, but to that point. And you find out that it's actually unstable, because any small random shock would completely drive us away from this equilibrium point. All right. How can we model such systems? Or how can we kind of represent these systems? How many of you are physicists here? Mathematicians? Has anyone heard of the gradient system? Gradient system? No, okay. Well, you don't need to. The point is the following. We assume, let's go back here. We assume that something could be a person, a ball, doesn't matter, something moves along this function, right? Let's say we put a ball here, and we let it go, and then what the ball will do, it will slide down. And this can be formalized with this notion of gradient, meaning that you have a potential this is the potential here, whose derivative equals your function f, right? We have an example in the next slide. But this is the intuition. We have a certain potential, like think of it as a landscape, let's say mountains, right? And then you put a ball or something on top of the mountain, you push it a little bit to the left or to the right, and then it will fall down, and it will settle at the basin. And this basically tells you that you follow the direction of steepest increase. So here it's a one-dimensional system. The direction of steepest decrease is just 1. But if you imagine a two-dimensional surface and you plot the surface, you may have, let's see if I can do it, you may have something like this, for instance. Therefore, the direction of steepest increase will have to be calculated by a vector sum, right? So you have x and y direction. You calculate the steepest increase in the x direction, the steepest increase in the y direction. You sum up the two vectors, and you get the direction that you actually go to. So this is the whole idea behind gradient system. You follow the direction of steepest decrease. Sorry. Okay. What we're interested in, let me go back here. As I said, are equilibrium points. And we can find the equilibrium points by just looking at the potential, looking at the landscape that our object moves on. And if we have a minimum of the landscape, so imagine a mountain, and like we have like this is the mountain, and here down there we have a basin. This is the a minimum, local minimum of our potential. That would be a stable point. The maximum of our potential would be very unstable. Again, unstable doesn't mean that you will never stay at this point. No, you will stay at this point forever. But if you're randomly perturbed, you will drift away from that point. All right. And this is the idea now. When you vary the control parameter, just a little bit, continuously, that's important. You vary the control parameter continuously, what you get often is that the number of equilibrium points changes. So from 3, you suddenly, and suddenly really means suddenly, it's discontinuous process. Suddenly you get 1, for instance, or you get 5. Also, the number of equilibrium points may remain the same, but their stability may change suddenly again. And this is what is referred to as the catastrophe theory, introduced by this guy, René Thom. So basically, he looked at this process as a kind of a catastrophe that occurs in our system. New stable states are generated suddenly or destroyed suddenly. And their stability also changes in this way. And of course, catastrophe is not in the popular meaning of catastrophe. He thought that this is a very drastic, very aggressive change in the system, and he called it catastrophe. But of course, it's not what most of us understand about catastrophe. This is and this is in fact, I'll show you a slide. It's what we call bifurcations, or forking. New stable points are generated or destroyed. So let's look at an example about this gradient system and moving on a potential. We have a potential function, which is this one. All right. Now, if you plot this function, assuming that u2 is 0, so your second control parameter for now is 0. What you get is this. This is the red dashed line. And this is plotted, I believe, for u1 equal to minus 50. So this is u1 equal to minus 50. This is, the next one is, yes, u1 equal to 50. Okay? So this is how your potential looks like for two different values of u1. But let's concentrate on the negative value first, minus 50. This one. So without looking at the equations, think what happens if you put a ball here. It will start following the direction of steepest decrease, so it will immediately slide down, and it will settle here. The same thing from that point. Right? So this is the minimum of our potential function, and it's a stable point. The maximum or local maximum of our potential is here, and you can imagine that if we have a ball here and we just push it a little bit to the left or to the right, it will immediately move away from that point. So this is an unstable point. And the speed of the ball is just given by this, by differentiating the potential and minus the derivative, of course. Okay, but now let's see what happens. So, right, we have two stable points and one unstable. So we have three equilibrium points or stationary points, two of which are stable, one of which is unstable. All right, and now we plot the same thing for u1 equal to 50. So we vary our parameter to 50. It's not a continuous change, as I mentioned. It's kind of a sudden change. We immediately change its value from minus 50 to 50, but what happens is this. All right. Now suddenly we only have one stationary point, right, where the derivative is 0 here, and it's a stable point because this is a local, it's in fact a global minimum for the potential. So you see what happened. From 3 stationary points, 2 stable, 1 unstable, we ended up with one stable stationary point. And that is what essentially is meant by bifurcation or catastrophe. We're going to work a lot with these kind of diagrams. Are they familiar to you? Has anybody seen such a diagram before? 1, 2, all right, 3. So, okay, this needs some explanation. What we're interested in fact, is to categorize what happens to the system precisely as we vary the control parameter. Okay? What happens to the stationary points as we vary the control parameter? So naturally you might think, well, we have to plot the control parameter versus the stationary points. And this is what's plotted here. This is minus u1. All right, it's minus u1 to make things more interesting. Basically, so that this can look like a pitchfork. You'll see why. I mean, it looks like a pitchfork, really. So minus u1. So this case here, when u1 is 50, minus 50, u1 is minus 50, would be here. All right. This is the point when u1 is minus 50. No, minus u1 is 50, therefore u1 is minus 50. You see, this is minus u1 on the x-axis. This is plus. Exactly. Minus is plus. Yeah. So that this can look like a pitchfork. If you plot it normally, then that thing would be reversed. You can still call it a pitchfork bifurcation, but it would be kind of not how it's typically displayed in textbooks. Or also to make things kind of more interesting, so that you play with the mapping of numbers in your head. All right, so this is 50. Well, what is it? No, this is u1 minus 50. This is, think of it as, it's inverted. So this is u1 50. Now, let's see what happens. When u1 is 50, meaning positive, we have only one stable stationary point, which is 0. And we display this. So on the y-axis, we have the number of stationary points. So the value of the stationary point, and the width of the line shows you their stability. So if it's a solid line, this means that the stationary point, this means that the equilibrium point is stable. If it's a dotted line, it means that the equilibrium point is unstable in the sense that I explained already. Small random shocks get amplified. So let's see what happens. We have one stationary stable point at 0, and we start increasing U1. Sorry, we start decreasing U1 from 50, 40, 30, 20, 1. Nothing changes. Of course, the shape of this thing would change, right? But the stable stationary point is still going to be at 0. Suddenly, at U1 equal to 0, something happens to the system. Look, this is a discontinuous process. 2 more equilibrium points are generated. And our point at 0, our stationary point at 0, now becomes unstable. It was stable before, now it becomes unstable, just as I explained, as I explained here. And this is a sudden change in the system. All right? And how you look at it is the following. Well, if U1 is minus 50, we have one stable stationary point here, which is given by something close to minus 5. Another one here, which is something close to 5. And unstable one at 0. At which one we end up, this is important, at which point we end up depends on the initial conditions. Right? If I start the ball here, it will end up at this stable point. If I start the ball here, it ends up at this stable point. So we don't claim anything about which of these would occur more frequently. It depends entirely on the initial conditions. And of course, you can calculate this these stationary points. If in case you're wondering why it looks like this, right? Like this. The reason is very simple, in fact. So if you look at our equation, minus 4x3 minus 2u1x, and then u2 is 0 for now, so we disregard it. We want this to be equal to 0, okay? This gives you 3 solutions already. X equal to 0, which is the unstable stationary point, and you have 2 more, which are given by, so x 1, 2, actually 2, 3. These would be no. Yes. Is it minus? No. By this. And it should be plus minus. Right? It's simply you solve this equation. X is one root equal to 0. The other one is plus minus should be here. Right? So one of them is valid when u1 is positive, the other one when u1 is negative. And the point is that this shape is a square root, and that's why the stable points look like a square root. Okay. This is a bifurcation diagram simply because it shows the bifurcations. And what you see at this point is the system transitioned from one single stable point, or monostability in a sense, to bistability, meaning you have 2 stable points now. And this is in kind of an elementary type of bifurcation. It's one of the most basic types, and it's called a pitchfork bifurcation because the shape looks like a pitchfork. There are other very interesting shapes like saddle knot bifurcation, which looks like a saddle for a horse. So yeah, it's quite quite basic. Now, this is also an interesting point: the application to decision processes. So imagine, for instance, you have your control parameter U1 is, let's say, the size of the population, the size of some population. So if the size is small, it's very easy for the population to reach consensus. So one stable point. But as you increase the size of the population, what you observe, what people have observed in real life, is that suddenly there is a polarization of opinions, right? Two left or right fraction, or conservative, liberal, doesn't matter what. Two opposing opinions emerge, and people have hypothesized that the process like this is behind that, with U being the control parameter, the size of the population. Oh, sorry for that. Yeah, so if you think about, it's the same system, by the way, an important thing. Here and here we have the same system, the same dynamical equation, but the behavior and on the outside it looks completely different. Now this is a little bit more intuition about what a bifurcation is. It's simply a forking, one solution into two. And in this figure you have one stable solution being forked into two stable solutions. Okay. And yes, an important thing to mention is that all these solutions are real. We're not concerned with imaginary solutions. All right. Most of the things, yes, so most of the things I've already mentioned. One thing to remember from all these slides so far, small changes in U, in the control parameter, they cause this kind of huge, people call them qualitative changes in the system, because kind of the quality of the system changes. Now let's make things a little bit more interesting. We assume that the second control parameter was 0, but what if it's not 0? Then we come into another bifurcation type, more interesting. First of all, what happens when U2 is not 0? Well, our potential is not this symmetric curve anymore. It's not this nice symmetric curve, but it becomes asymmetric, which means that one of these kind of wells is removed or shifted. And here we've plotted U1, again 50 or minus 50, so this is the red one is U1 minus 50, and U2 is positive. What is the value? Yeah, it's 200. So U2 is positive here at 200. Here U1 is positive 50, but U2 is negative minus 200. And we're interested, so we fix U1. Let's say, what is it fixed to? Oh no, sorry, I was confused. U1 is minus 50 in both cases. Here and here. We fix one control parameter and we start to vary the second one, which is U2. So what happens? Don't look at the bifurcation diagram yet. Let's say we start from this point. All right, so we have this kind of a potential. Like here we have this kind of well, which is almost destroyed, and here we have our normal basin. When you start to vary U2 to increase it, what happens is, right, so you start with, you start with 200, you start to decrease it. At 0, you get the symmetric potential, and when U2 gets negative, the wells basically change. So one of them becomes, right, so look, this one becomes now a proper well, proper basin, and this one gets almost destroyed. All right? And you can imagine here, if we keep increasing U2, we don't start decreasing it, but we keep increasing it, eventually this kind of stationary point will slowly, completely lose its stability. Right? This will just become like a line. There would be no well anymore. So the stable point will be destroyed. The same thing here. And the bifurcation diagram is very interesting. So U2, let's start with U2 minus 200, which is basically the red curve. What it tells you is that we have only one stable stationary point at, I don't know, 7 point something, which is this one. U2. Oh, okay. So we're looking at the black curve. Right, minus 200. We have this stable point. This is stable point. This is not. Right, we destroyed it. Now, if you put a ball here, it will start rolling. It will not stop here. You know, there is no well anymore. If we keep increasing U2 from minus 200, we slowly keep increasing it. What happens is the system moves along this line. So we still have one stationary point, stable stationary point. At this point, we have 3. So as soon as U2 crosses the minus 100, I don't know, 70 something, we have 2 stable stationary points and 1 unstable given at this value. So what happens is we start here and we start increasing U2. So we have no well here, we destroyed it. We have a well here. When we keep increasing U2, we'll slowly form a well at this point. This thing will get a little bit destroyed, the other one, but it would still be kind of a well, right? So it could still be stable. If you plot, if you plot this function with minus 100, for instance, you would see that you have 2 wells. One of them is bigger than the other one, certainly, but they're still wells, stable points, and at 0 we have unstable point. Right, so here, as we keep increasing U2, now this is the funny thing which happens. Imagine we're at this point, right? We keep increasing U2, we have 1 stable point, 1, 1, 1, 3 equilibrium points, 3, 3, 3, 3, and suddenly the system jumps from here, and moves in this direction. So from 3, here we have 3. At this particular point where the solid line and the dashed line kind of touch each other, these 2 points annihilate each other. So that solution, this well, and the 0 kind of annihilate each other, and they disappear. And we're left with only 1 stable stationary point here. Now, the interesting thing comes now. What happens if we start from this point? Remember, we varied U2, and we went like this. Here, and then we jumped here. If we start varying U2 from here and we start decreasing it, we move like this. At this point, you would expect to jump back here, right? Because when we swept the whole thing from left to right, we did it. But when you sweep it from right to left, you don't jump back here, but you keep going in the same way, and then jump back here. And this is called the hysteresis effect, right? Because going from left to right is not the same as going from right to left. And you can imagine, so there is this book given in the notes by Eli Kianch. It's a very nice book, The Self-Organizing Universe, and it's really a pity that it's almost out of print, because it's, I got it from the library, but it's a very intuitive book, I would say. There is not incredible amounts of mathematics there. But what he says is, well, that this hysteresis effect could be could model the so-called Hawk and Dove populations. What this means is the following. We have, or let me first give you another analogy, the angry dog analogy. So you have a dog, and you try to stress the dog. So I'm not saying I did it. You probably should never do it also. But in case, just think about it. So you start stressing the dog somehow, right? Let's say here. And you start stressing the dog maybe doesn't respond too aggressively. It kind of barks a little bit, backs into a corner, but nothing particular happens to the dog. So you start stressing it, and here at this point, so after the stress that you apply to the dog passes a certain boundary, and this boundary is given here, then the dog goes completely berserk, goes crazy, right? So it's kind of the dog jumps from here to here, so the behavior completely changes. And now if you start decreasing the stress, it is not the case that when you decrease the stress here, so imagine you increase the stress up to here and the dog is really crazy. Now you start decreasing the stress. It's not the case that when you go back to that value, the dog would become calm again. No, you have to decrease the stress more here in order for the dog to become calm. This is the hysteresis effect or the memory effect. The dog somehow remembers, has some kind of residual memory, so that you need to do more work in order to eliminate this memory and go back to the calm state. And the hawk-dove example is similar in the sense that we have a country which, for whatever reasons, wants to invade another country. We had this happening, at least in my lifetime, a couple of times. And imagine the population is split in two fractions, hawk and doves, basically. The hawks, they want to attack, national security issues, all this kind of stuff, weapons of mass destruction, doesn't matter. And the doves, they just want to, want to have peace, they don't want any war, right? So imagine this state, for instance, corresponds to a population where you have a lot of doves and just a few hawks, right? So the country as a whole will not go to war because most people don't want to. But then, due to some external influence, maybe media effect, maybe propaganda from the government, who knows? The population of doves start to slowly decrease and the population of hawks start to increase. At this point, when the amount of, let's say, media propaganda has become too high, suddenly the country goes to war. Suddenly what happens is the population of hawks just explode, so they become a lot, and the doves, they become very little. Now, if you start decreasing the media influence, again, as in the case with the angry dog, it's not the case that coming back to that point would bring the things to normal. So hawks would decrease, doves would increase. No, you have to decrease the influence a lot more so that your population returns in a calm state as before. The idea is memory effect. So these systems have memory. You apply certain force from one direction, from left to right in this case, but then when you start removing this force, the system remembers there is a residual force left into the system, which you have to basically counteract with even with more counter force. That's the whole idea. And this happened only when we allowed for two control parameters in our very simple system. This, in fact, is called cusp bifurcation. And in 3 dimensions, it looks like this. Right? So these are the two control parameters, and these are the stable points. So see, here we have just one stable point. Here. But this is exactly, this thing is exactly what I showed you here. So now imagine we put a ball on top and you push it a little bit to start rolling. Actually, you don't even need to push it a bit because this is not the equilibrium point. What the ball will do, it will start sliding, and then suddenly jump here. Right? Just as I told you. Like the ball slides, and then jumps here. This is the cusp bifurcation. And you see, by varying the U1 now, we can decrease this range. Right? We can decrease this this range. So this thing, the dotted line becomes compressed, more compressed and compressed. And in fact, here, we almost have a singularity. And beyond that, it disappears, this effect. So this is another very famous bifurcation. It's called the cusp bifurcation. And these are the only 2 bifurcations that we'll be dealing with. All right. Now, so far so good. Can you tell me how much time is left until the break? Because this display is broken. 5 minutes. All right, so we'll have time for one more slide. I have a question for you now. So far, we've only seen systems in continuous time, right? This was x dot, the dynamics was given in continuous time. The S-curve technology adoption from last time, it was again continuous time. But of course, in real life, most systems are, what are they? Yes, they are discrete. Why? Did you answer? Because? Intuitively, because there's only so much, there's only a finite amount of kind of separations that you can split a human being into, for instance. You cannot have half a person, for instance, right? Or you cannot have 0.0000001% market share. All right. So basically, yes, in most cases, the real life systems are discrete. And now, I'd like to investigate the population dynamics system that we saw. It was given in continuous time, remember? It was this, the population growth, x dot, is equal to the net birth rate, and then there was some crowding effect. But this was a continuous time system. In real life, of course, this would be a discrete time system. You know, you cannot have half a rabbit. And then we'll see that, amazingly, when you go from continuous to discrete time, new things can happen to the system. New things in the sense of critical points or equilibrium points. And in the end of the lecture, you'll find out that chaos can occur in a discrete system, but not in its continuous counterpart, which is a curious thing to know, because depending on how you model your problem, you know, if you model your problem in a continuous way, you lose an important ingredient. And in fact, when you write, especially in academia, when you write papers and you propose models, people are very sensitive to why you chose to model continuous system and not discrete system, because you lose important things, and you'll see what we lose. All right. Quick introduction to discretization, how we discretize a continuous system. Well, we start with the ordinary differential equation, which is given by this. You know, x dot changes according to some nonlinear function f. And now what do? We, let's start from here. We define a time step, right? So continuous means, in theory, continuous means that at infinitely small time steps, the system is defined. But of course, we cannot have infinitely small time steps. We have a finitely small time step. There's only so much you can split the time. All right, so let's discretize the time. Let's say T0 is the first time step that our system is defined. T1 is the next smallest time step that we can define. Let's say T1, and T1 would be equal to T0 plus, yes, 1 times delta T. And delta T is your time step. If for some reason you believe that in the universe time can only be split in time steps not lower than 0.1, then 0.1 would be your time step delta T. And what you do now is the following. The value of your system in the next time step, T plus delta T, is the value of the system in the previous time step plus how much it changed. Well, how much it changed is given by the first derivative here. Yeah, we'll continue after the break then. But I think, all right. So I was going to show you how to discretize a continuous system. Now remember, we have what we're interested in is this value. What is the value of our state variable in the next time step, t plus delta t? So if you do something which is called Taylor series expansion. Taylor series expansion meaning you simply linearly approximate the function, or not the function, but this value. You linearly approximate it in the vicinity of that value, right? So we approximate. Well, actually, I have to draw it. So imagine you have this function, for instance. If you're interested in the value at that point, at that particular point, the Taylor expansion allows you to linearly approximate that value by using the first derivative of the function. So if you draw the first derivative here at that particular point, you can use the first derivative as a very crude method of approximating that value. Now, if you want to calculate that value, you cannot use this, of course, because look, the first derivative is here, and this is your value. You need to, again, use the first derivative here. Now, again, this would work relatively well if the function is smooth. You know, it's well behaved. You take the first derivative, and it's more or less looks quite good. Of course, if it's not, if it's very rugged, like I don't know, something like this, then at that point it's kind of difficult. But for now, we assume that the function is sufficiently well behaved. So we approximate this x of t plus delta t. We expand it, in other words, we do the Taylor series expansion around t, around this point t. Right? So let's keep our picture. If this is t, this is our t. We're interested what happens at t plus delta t, and delta t is very small, let's say here. This is delta t. You can't see it properly. Right? Delta t is here. So you can say, well, I can still use this first derivative at point t to approximate that point here. Right? It won't be very accurate, but for a sufficiently well-behaved function like this one, it's kind of closed. You see? The actual value and the first derivative are kind of close to each other. So we can use this. And the Taylor series expansion is basically equal to, you can look it up, how it's computed, but if you compute it, it depends on the value of the function at the point around which you're expanding it, t, plus the first derivative, so this thing, times delta t, and then here we have higher order terms. So if you want to take higher derivatives, not just the first, but maybe the second and so on, you can do it to make it more accurate approximation. But if delta t is sufficiently small, then delta t squared would be even smaller, so we can safely ignore that term. The error would not be that big. But what is this? It's basically, now if you assume that delta t is 1, we have that x of t plus 1 in the next time period is equal to x of t plus the first derivative. And this is called the Euler integration method. If you numerically integrate this, using the Euler method, this is the Euler method. It doesn't work for exponential functions, so don't use it. If you have an exponential function, so If you have this, then the other method doesn't work. It will work if you have very, very, very small time step, like very small, 0.001 for instance. Because the error is just too big. You only take the first derivative. And you know the exponential grows really fast, right? So if you right, the exponential grows really fast. So we want it to be here, t, this is t. Delta t is probably here, t plus delta t, sorry. But since this is an exponential, these 2 points would be very different. You know how the exponential is, right? You increase the x by a little bit, and then the value of the exponential changes significantly. So these 2 points would not be that close as you think, which means that either this distance has to be very small, meaning delta t has to be very small, or you have to use a different integration method. Runge-Kutta, for instance, is a good one. But this is how we discretize a continuous system. It's very simple. What happens in the next time step is the sum of what happened in the previous time step plus the derivative, plus how it changed. Right? This is where I was in the past plus what I did to get from the past to the future. All right. And as I mentioned, doing this discretization, even if you do it properly, can introduce new behavior, in particular chaos. We'll look at that. Oh, sorry. Now let's look at the population growth from 5th lecture, I believe. Remember, by the way, this is n dot. Please mark it in your slides, n dot. So the rate of change of the population. The rate of change of the population, or I think it was the rabbits at that point, there is a birth rate, right? And there is a crowding effect. You remember this. I think the parameters were named differently, but the idea is still the same. We have some birth rate, but eventually the influence of the finite environment would generate this kind of S or saturation behavior. So this was how our rabbits grew. And n here is, let's say, the number of rabbits, for instance. All right. And now you know how to actually calculate stationary points, right? We did it for the rabbits. It was either 0 or k over m, but now you know how to do it, right? You just set this to 0. This is when the population doesn't change anymore. And obviously n equal to 0 is one solution. The other one, since this is a quadratic equation, the other one would be k over m. We haven't said anything about how these solutions are reached, right? Whether we reach the solution like this linearly, or it's kind of a saturation, or oscillations, and then we reach the solutions. That's not so important. The stable points, that's not so important. These are the stationary points. Okay. And we also use something like this to generate an S-curve. This is called the logistics growth. The logistics growth, and in fact, this is how, you'll see that in the next few slides, but this is how bacteria grow. It can be shown that this is how bacteria grow. Well, let's discretize it now. So we just do some change of variables. T is now n, and we define xn to be this. We also, so what we want to do is to eliminate these parameters, k, m, and n. Because if you think about it, this is 3 control parameters. We just want 1 to simplify things. So by just redefining the variables, we define, right, so let me show you. How do we get this? Is it obvious to everyone how we got this? Remember, n of t plus 1 was equal to n of t plus the first derivative. But the first derivative is k times n of t minus m times n of t squared. Okay? Which is simply equal to k plus 1 times n of t minus this. Okay? It's simply applying what we saw before. This is how we arrive to that equation. We define now k plus 1 to be equal to r, just to make the notation simpler. So we have one control parameter. We define xn to be this. And finally, this is our equation in discrete form, right? It's also called the recurrence equation. Or, yeah. So, does this look familiar? Has anybody seen something like this before? Well, in fact, this is what people call the logistics map. From the logistics growth, we discretize the logistics growth, and we got the logistics map. And this, look, it's so simple. It looks very simple. It can generate amazingly complex patterns, and I'll show you this now. Right, so logistics map is given here. If you just look at how two subsequent values of x are related, well, they're related in a quadratic way, right? So this is xn squared, right? So if you plot xn versus xn plus 1, you see that xn plus 1 reaches, so the next value, reaches its maximum when xn is 1/2, right? So if this is 1/2, this is 1/2, times 1/2, 1/4, r over 4. So the maximum value is given by r over 4. And if we increase xn, the subsequent value is lower, actually. So this is just how xn is related to xn plus 1. More interesting is this picture here. Let me explain you how we do it. This basically gives you a graphical intuition or graphical way of how that system would develop over time, how the xn would develop over time. So we start with some random x0, some initial condition, I don't know, x0. From x0, we calculate x1, okay, by this formula. We calculate x1. From x1, we calculate x2. From x2, we calculate x3. From x3, we calculate x4. From x4, we calculate x5, and so on. So you see that if you look at this progression of the x, it eventually reaches a stable point, which is given by xs. Sorry, stationary point. xs here. If you start from a different initial condition, or your r is different, I don't remember exactly what r is this here. But if your initial condition is different and r is also different, then you would get a different dynamics. You won't get this. This is a very nice stable behavior, right? The system converges to a value eventually. But this need not be the case. And you'll see that. All right, let's investigate now the role of the control parameter r. We only have one control parameter. So if r is between 0 and 1, what would that mean? R is between 0 and 1. Remember, we had k plus 1 is equal to r, just without calculating any math, just intuitively. K plus 1 equals to r. If r is between 0 and 1, this means that k is negative, but k was your birth rate. So if the birth rate is negative, the population dies out, and nothing happens. And that's why the stationary state is 0. There are no rabbits in our population. You don't need to plot anything. If r is between 1 and 3, this is the stationary state. The stationary state is given by this value. So we slowly converge there. And this is a picture how we converge. So R is 2.8, is between 1 and 3. And we start with this initial condition, 0. I don't know, some initial condition. We have some oscillations until we finally converge to our value 1 minus 1 over R. Is it clear how we calculated this? Wait a second. Yeah, this is the slide. Why is that the stationary state? 1 minus 1 over R. Let's see now. Yes, I'll go to that side. So what does it mean for a stationary state? What does a stationary state mean? Well, it means that if we have no random shocks, we don't push the system, it will stay there. Which means that xn plus 1, was it n the index? Yes. Would be equal to xn. Okay? You can even say this. Xn plus 2 would be equal to xn plus 1 to xn to xn minus 1 and so on. Right? Because the system will always stay at this stationary state forever unless you shock it somehow. So we start with this, but xn plus 1 is also calculated by our recurrence equation, R times xn 1 minus xn. Okay? So we simply make these two things equal. So R times xn 1 minus xn is equal to xn. Xn cancels, and you're left with the stationary state is there. Okay? That's how we calculate the stationary state. If R is between 1 and 3. Now, why between 1 and 3? It can be shown, but let's not concern ourselves with this. It's not so important. When R is between 3 and 4, we have oscillations. And this is for R 3.3. You see, we start with some, I think it's the same initial condition. And after some kind of time where oscillations grow, we have stable oscillations. So what you have is xn and xn plus 1 oscillate like this all the time. And this is also called a two-period cycle, right? Because the cycle has a period of 2, right? 1, 2. 1, 2, the same cycle. Let's move on. If R is 3.5, we suddenly have, again, oscillations, but the period is now of length 4. It's a so-called 4-period cycle. And it's a stable cycle, right? So unless you shock the system, it will always oscillate like this. Look at this, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. It's the same cycle all over again. Which means that if you know that, you don't need to compute the values for n for n 200, for instance. You can immediately say, well, it's a 4-period cycle, so it must be one of these 4 values. So look what happened. From a 2-period cycle for 3.3, we went to 4-period cycle for 3.5. This is called a period doubling. Right? When you increase R, you double the period of the cycle. And it can be shown that as you increase the value of R, you double the cycle, the period of the cycle in this way. At 3, we have a period of 2. At 3, 4, 4, 9, period of 4, 8, so on and so forth. And this is interesting. At R value 3.569, infinite period. What does that mean? Any intuition? Yes? No. On the contrary, there are oscillations, but the period of these oscillations is infinite. What does that mean? Yes?
There is no pattern anymore.
Yes, that is true.
Stochastic behavior?
Yes, that's how it would look like, but for reasons that will come apparent in the next 2 slides, I would not like to call them stochastic. Simply because, look, this dynamics is completely deterministic. There is no stochastic influence anywhere along the dynamics. And this is the amazing thing, actually. This is a completely deterministic dynamics, and yet you get a cycle of infinite length. So this is actually what we refer to as chaos. Right, so this was it. Yes, so 3.9. When R is bigger than 3.57, yes, so we have this kind of infinite period, cycle of infinite length, but yeah, windows in the chaos. I have to show you the bifurcation diagram for you to understand that. For now, don't think about the windows in the chaos. just think of this. This is R 3.9. This is an infinite period of infinite length. So the cycle has infinite length. There is no period, basically. You can't find a pattern here. When R is equal to 4 and larger, is it larger? Yes. Then you have fully developed chaos. We'll find out what fully developed chaos means. Basically, we distinguish between fully developed chaos and chaos with windows. And it becomes more apparent when I show you the bifurcation diagram. But for now, look at this. So this is cycle of infinite length. And if you remember that very nice picture that I showed in the beginning, we start with some value here, and we basically move randomly around this map. Right? There is no fixed pattern. Now, this is the bifurcation diagram. This is R and this is X. It's slightly different from the bifurcation diagram that I showed you before. And at least when I came across this, it confused me a lot. Because remember, the bifurcation diagram shows you the stationary points. All right? If you remember our nice bifurcation diagram, one stable point, one stable point. The system can never be at these 2 stable points at the same time. It can only be at 1. And it depends on the initial condition at which one we end up. But here, when we have oscillations, the system actually oscillates between 2 stable points, for instance. And this is how we illustrate it. We have 2 stable points, for instance, here and here. But it's not like before, where only one of them can be, the system can be at only one of them at any given time. No, we oscillate around these 2 points. And that's why this is not X stationary, but it's just X. So this is oscillations between this point and this point forever. But let's start from the beginning. When R is between 0 and 1, birth rate is negative, everybody dies out, 0. When R is between 1 and 3, I believe this is 3. Yes, it should be 3. Again, we only have one stable point, and it's this one. How we reach this point, we don't know. Maybe we reach it through dying oscillations. Maybe we just go to it as an asymptote. I don't know. But this is one stable point, and for each particular value of r, we can calculate it. Funny thing happens at r equal to 3. If you remember, we double, or we generate a cycle of length of period 2. So this is a cycle now. The system would oscillate here and here, here and here. At r equal to, I don't know, 3 point something, it's written in the slides, we double the cycle. So we have a period of 4. So the system oscillates between this value, that value, that value, and that value forever. And now what happens is, if we increase r beyond this value, it's again given in the slides, or beyond this value, look at what our system does. Oh, I mean, I cannot show you, but let's be here, you know. So the system would just go randomly to basically any value on the 0, 1 interval. It's not nice oscillation like here, but any of these values can be chosen. And this is a zoomed in picture from 3.62 to 3.65. This is chaos, okay, here. So basically xn and xn plus 1 would be completely random, no patterns at all. But suddenly, as you keep increasing r, the picture changes again. So from chaotic regime, we get to something which is 1, 2, 3, 4, 5. It's a period of 5, right? So it's an oscillation, and there are 5 stable points. This one, that one, that one, that one, that one. So the system would oscillate between 5 values. This is called a window in chaos. So we have a chaos, and then we have kind of, it looks like a window, right? As we keep increasing r, we go back to a chaotic regime, where any value on the 0, 1 interval can be chosen. Here we have another window, very small, but yet another window with 1, 2, 3, 4, 5, 6, 7, 8, period of 8. And beyond that value, we only have chaos, or in other words, fully developed chaos. This was the meaning of a fully developed chaos. There are no windows anymore. All right. Well, people have studied the logistics map for a good 30 years. And it can somehow be shown mathematically even. Analytically, I mean. You don't need to compute forever. That's the point. All right. By the way, if you look at the book, it's given in the notes. Slide 11. It's the Strogatz book. It's really good. It has a lot of explanations about the logistics map. But this is this is the meaning of chaos with windows and fully developed chaos. Now, I am still a little bit hand-waving here about chaos. Probably still you don't have any idea what chaos is. Yes, we have no pattern emerging, but an important thing is that if you look at this trajectory, for instance, we start with x, let's say we start with some x0, some initial value. And then for r equal to 3.64, you end up here. I mean, you can calculate this actually. If you start calculating, you calculate an r equal to here. You know, there is no actually chaos at all. If you compute your system, everything is fine. You will know exactly what will happen in the long term for r equal to 64. Let's say after 100 time steps, you calculate it, no problem. But what happens if your initial condition is slightly off? If there is a little uncertainty in your initial condition. So instead of x0 equal to 0.1, let's say you have x0 0.1001, for instance. You will not end up here as you have calculated before. You will end up at a completely different point, maybe here. Okay? And this is the notion of divergent trajectories. Nearby trajectories diverge. So nearby initial values, infinitely close to each other, they would result in completely divergent long-term values. And the only way that you can now be sure what your value is to calculate it again. right? You cannot make predictions, that's the point. As you mentioned at the beginning, you cannot make long-term predictions because given a very small amount of uncertainty in the beginning, you end up at a completely different state. And this is the idea of divergent trajectories here, right? You start with very close initial conditions. And I mean, in real life, you can never be 100% sure about anything. So you always have some uncertainty, especially in your initial conditions. You end up at a completely different states. And yeah, that's the idea of divergent trajectories. And this is yet another definition, ingredient of chaos. And now, what actually chaos is, we have all the components to create a working definition. It's not a mathematically strict definition, but it's good enough for us. First, we have aperiodic long-term behavior. As we saw, cycle is of length, the period is of length infinity, right? You have no pattern. But that's not enough. The system generating this behavior must be deterministic, okay? Like in our logistics map. There's no random input, no noise, nothing. It's completely deterministic. And divergent trajectories, meaning sensitivity to initial conditions. Two very close initial conditions end up at a completely different points. And now the question is, well, how do we know that a given sequence of numbers, for instance, is chaotic? Right? It may be just that the period is of length 128. It's still periodic. The period length is very high, but it's not chaotic. It may look like chaos, but it's not. And there is actually a mathematical kind of approach to this. We calculate the so-called Lyapunov exponent. Have you ever heard of this? 1. All right. It's very simple. The idea is the following. Let's see what happens if we introduce a little bit of uncertainty in our initial conditions. So we don't start at x0, but we start at x0 plus delta 0. Right? So delta 0 is the amount of, if you'd like, the amount of shock that you give the system. So you push your initial condition to the left or to the right by the amount of delta 0, and that delta 0 is very small. What you're interested in to know is what happens to this initial fluctuation, to this initial shock. Does it grow or does it die out? If it dies out, then we say there's no chaos here. If it grows indefinitely, then we say that it's chaos. And remember what I told you, exponential divergence of trajectories. We simply define that we want the trajectories for chaos to be exponentially divergent. We define this. Not linearly, but exponentially. So we say, okay, our initial fluctuation after n time steps would develop like this exponentially. So if lambda is positive, then our initial fluctuation would have grown exponentially, right? So the final deviation, delta n, would be exponentially bigger than the original one. And if lambda is negative, then the initial fluctuation would die out. And the lambda is called the Lyapunov exponent. Right? So you have, well, here. So f, you apply the function f. All right, let's start from here. Let's just go here. We want to know what happens to the final fluctuation at time step m. Well, it's simply equal to, so what this notation means that you apply your map f, or your function f, you apply it n times to the initial condition, right? You start with x0, you apply this function once, you apply it twice, 3 times, 4 times, 5 times, right? So you apply, we start with this x0 plus delta 0. Remember, we have this small fluctuation. We apply our logistics map n times, and this is where we end up at the end. We subtract from this the value where we were supposed to be without any fluctuations. So just start with x0, no fluctuations, end up somewhere. And we look at the difference. If that difference, delta n basically, is very big, so first, let's compute it before talking about big or small. Let's compute this. What is the difference, delta n? Well, if you take the logarithm of these two things, you get that alpha is equal to 1 over n, natural log of this. Now, you substitute delta n to be equal to this. There are a few steps that are not shown. I hope we'll have time to show it. All right. So, now, we won't have time. I won't have time to show you this. It's just 2 lines which are missing. But in fact, what happens is you substitute delta n, this value, you substitute it here, and then this, imagine this, you divide by delta 0. And if delta 0 goes to 0, this is simply the derivative of f at x of xn. Yes. Yeah, I have to show you this so that you can understand, but let's leave this for either after the lecture or during the self-study because we don't have time now. And don't worry, this is not an exam material. It's just to give you an idea. This is how we calculate the lambda, and now this, if that thing is positive, we have chaos. If it's negative, we don't have chaos. Why is this interesting? Well, this is your time series, right? You have your time series, xi, from 0 to n. You can compute, you know how they changed, what the dynamic is between x0 and x1, or x1 and x2. So you can compute these things. You compute this value. If it's positive, you have chaos. If it's negative, you don't have chaos. It's a very simple way to to do this. And this is the same picture as we saw before. The logistics map is chaotic here. You see the Lyapunov exponent is positive. Windows in the chaos, Lyapunov exponent gets very negative. Again, chaos, Lyapunov exponent is positive. Another window, negative. All right.
Now, application.
Is it true that we have 1 minute left? 5. Okay, that's good. That's good. So, we have a manufacturing system. This is an example of chaos in a manufacturing system. I talked about this in the beginning of the course. We have a manufacturing system, and it exhibits chaotic behavior. So, unpredictable behavior in, I don't know, utilization of some machine, for instance. Whose fault is it? Is it the manager who is not creating the proper processes, or is it just the property of the system itself? This is an example now to the end of the lecture where we'll see that it could be the property of the system itself. So we model our manufacturing system in the following way. By the way, I forgot to print this slide, so I don't have a handout. We model the manufacturing system in the following way. We create the notion of a buffer here, which is basically things that get filled or emptied over time. Right? You can model a lot of real manufacturing entities like this. For instance, a manufacturing line on which some parts flow. You can model this as a buffer which needs to be full at all times. Right? A manufacturing line has to be full or occupied the whole time. Otherwise, it's underutilized. So we kind of abstract a real manufacturing system with the notion of this kind of buffers, right? So we have buffers. They could be emptied or filled, and they could be emptied or filled just by one entity. So we cannot empty or fill them in parallel together, but just one entity has to go to each buffer and empty it, for instance. Right? So one person has to go to each line and do something. And this is our setup. We have these buffers. We don't want our buffers to get overfull or to be empty. So you don't want parts to be falling off from your production line because it's too full, but you also don't want this line to be empty. And the question is, what is the optimal strategy for someone, a person for instance, who goes around and services each buffer, each line? This is not important. These are two different ways to look into the problem. I mean, that slide is simply explanation of these pictures. We can have these buffers, which are filled by independently by rates of lambda 1, lambda 2, and so on, but they're emptied by one person. In this example, it's not a person, obviously, it's kind of a machine which goes to each buffer and empties it when it gets full. We don't want the buffers to be overflowing. And this is the so-called server. This thing is the server, which goes around each buffer and empties them. And the analogous situation is when the buffers are emptied by themselves. Say they have a little hole in some container has a little hole, so it's emptied at a given rate, and you don't want containers to be empty. So a server would now go to each buffer and fill them when they get empty. So this is called the switched arrival system. This is called the switched server system. We'll be considering the switched server system. Now, what are the rules according to which that server has to visit each buffer and empty it? These are the rules here, but okay, this is the picture, right? We have a real manufacturing system, and we abstract it into these so-called buffers, buffer, and we have a server here. This server is like a machine which goes and visits each buffer. Again, we're concerned with the server system. The arrival system is completely the same. The server system, if a tank, so remember the server system empties the tanks or the buffers. They're filled by themselves, by someone. So if a tank gets filled to the maximum, then obviously the server has to go and service it. However, if the currently served tank, so here, if the currently served buffer, so while you're emptying the buffer, some other buffer gets full. You have to stop emptying this buffer and move to the other tank. However, if while you're emptying your buffer, nothing gets full, then you empty it until the end, 0. And if still nothing is full yet, then you simply move to the next one in the sequence. So from buffer 1, you move to buffer 2. Right? And this is what it says here, in a cyclical order. Right? So while you're emptying something, if something else gets full, you immediately go there and start emptying it. If not, when you're done, you just move to the next buffer. Yes, let's skip that. Okay. I forgot to mention that we have a capacity B of our buffers. So this is the size of liquid or machines or parts, whatever, that our buffers can support. So 2-3 more minutes. So B is our control parameter. We have only one control parameter in this system, B. These are equations telling you how the level of the liquid in your buffer changes depending on whether it's being serviced by the server or not. It's very simple. But the interesting point is here. So we have 3 servers in this example. Sorry, 3 buffers in this example. 1, 2, and 3, or x1, x2, and x3. If we start at this point, what is this point? x1 is relatively full. x3 and x2 are relatively empty. So the server is here. The server starts emptying buffer 1, right? It empties this, emptying, and finally we end up here. x1 is completely empty. x2 has got full, a little bit full in the meantime, and x3 also got a little bit full in the meantime, right? We were just emptying the first buffer, but the other 2 were being filled with these rates, 0.5 and 0.4. So we end up here. If we start from that point, x1 is, somehow full. x3 is also kind of full. x2 is empty. So we start emptying x1, x3 and x2 would get full, or fuller. All right? So you see what this diagram means. This is the server movement. Now, what happens? We start at 1, we're emptying buffer 1. Now we're here. Buffer 2 is kind of full. Buffer 2 is kind of full. Buffer 3 is not empty, but not as full. And buffer 1 is empty. So now we're emptying buffer 2. Now we're emptying buffer 2. We start emptying buffer 2. Buffer 1 and 3 will get full, right? We move here. So buffer 1 is now a little bit full. It was 0 before, now it's a little bit full. But buffer 3 is even more full. And now the logic is that now the server starts emptying buffer 3 because it's almost full. So if you look at the dynamics of or the movement of the server, it moves like this. I empty buffer 1 here, buffer 2, buffer 3, buffer 1, 2, 3, 1, 2, 3. It's very nice, predictable sequence of how your server moves and how your buffers, the liquid or the fullness of your buffers develop. This is if the capacity is 1 of your buffers. If you decrease the capacity to 0.5, just decreasing the capacity, keeping the same rules, look what the server does. It's completely crazy, right? You start emptying 2, 3, 1, 2, 2, 1, 3. No, this is the chaos that we're talking about. The movement of the server is completely unpredictable. It's not nice as here. And these are the bifurcation diagrams. This is your control parameter B, the capacity. This is the level of the liquid in each of the 3 buffers. So if the capacity is 1, the first buffer would start getting emptied when its level of liquid is 0.1. This buffer would start getting emptied when the liquid in it is 0.6, and this is 0.7 or something. This is nice. But here, the buffers can start getting emptied at any point of time. It's completely unpredictable. Yes, so in the beginning of the next lecture, I will go back a little bit in more details to these slides, especially these equations, in case you find them confusing. But this is I hope you got the idea of the chaos which emerges. Thank you. That x, your state variable x, would increase in the next time period. So we'll be pushed again back to 0. So even by looking at the way that the nonlinear function f crosses the x-axis, you can kind of intuitively guess whether the point is stable or not. And this is actually how stability is defined. Small random shocks die out. They don't get amplified, they die out. And this is what happens here. We'll go back here. And as an exercise for you, even now, you can apply the same logic to that point. Not to that point, because we don't know what happens here, but to that point. And you find out that it's actually unstable, because any small random shock would completely drive us away from this equilibrium point. All right. How can we model such systems? Or how can we kind of represent these systems? How many of you are physicists here? Mathematicians? Has anyone heard of the gradient system? Gradient system? No, okay. Well, you don't need to. The point is the following. We assume, let's go back here. We assume that something could be a person, a ball, doesn't matter, something moves along this function, right? Let's say we put a ball here, and we let it go, and then what the ball will do, it will slide down. And this can be formalized with this notion of gradient, meaning that you have a potential, this is the potential here, whose derivative equals your function f, right? We have an example in the next slide. But this is the intuition. We have a certain potential, like think of it as a landscape, let's say mountains, right? And then you put a ball or some. So let's get down to it. Role of control parameters. I will introduce a few basic notions first about what is a dynamical system and what kind of things we're interested in a dynamical system. What we're interested in is this, basically. This is the equation that governs the evolution of a dynamical system. I mean, why is it called dynamical in the first place? Right? I mean, because we're interested in its dynamics, in its rate of change. This is the first derivative, basically. How it changes over time. And we assume, for all the systems that we saw so far, we assume that the way that the system changes over time depends in some nonlinear way on its current state and some control parameter. Now this is our control parameter. Of course, I mean this could be a vector of control parameters. It doesn't have to be one. It could be many. But things get more complicated, especially if you try to plot the phase space of a system with, I mean, 3 control parameters. You can't do it. You need 4-dimensional picture. All right. And when you have a figure like this, right? So this is the current state of the system, and that is the way that the system changes. And let's say this is the nonlinear function. All right. What are the points of interest? If you look at this figure, what are the points of interest? For nonlinear dynamics, the points of interest are the points where the system is stationary, so it doesn't change anymore. When would the system stop changing? Well, obviously when the first derivative is 0, when its rate of change is 0. So this point here, and this point here. These points are called stationary points. ST, this here. It's not stable. Okay, good morning, everyone. Speaking about disease spreading last week, I've managed to catch one. So I apologize in advance if today is not going to be the best performance ever. But fortunately, the lecture is somehow easy to follow. So there is not going to be too much, hand waving and stuff. All right. So this is the 10th lecture. No, what? No, this is the 8th lecture. It's the 10th of November. Yeah. Question to you: what did we do so far? Let's say last lecture. What did we do in last lecture? Does anybody remember? Modeling, yeah, I mean, we've been modeling already 3 lectures back. We've been modeling disease spreading. That's why I got one. We looked at technology adoption, the S-curves. And we tried to model the technology adoption, and we used this famous model of disease spreading. Susceptible, the SIR framework: susceptible, infected, and recovered. Okay, sorry, I have to move here. This idea of modeling technology adoption is basically applied to market growth and to any kind of product or anything that penetrates a market, for instance. We also looked at the inventory model. This was 2 lectures ago. And for all these models, we investigated how small changes in whatever parameters, we talked about control parameters, what they could be, and how these small parameters can influence the dynamics. But today, we're going to be to introduce more formally what we mean by varying a parameter and observing a change. So far, we did it kind of heuristically, right? We change a parameter, and you see in Vensim, okay, some amplitude increases, or 2 things become suddenly uncorrelated. But today, we're going to be looking kind of mathematically what happens when you vary control parameters on the system's behavior. We'll define exactly what system's behavior is. And this is going to be also an introduction to chaos. So, before we go on, can I ask you, what is your opinion? What do you think chaos is? It's not a question which has a right or wrong answer. I just want to get an idea what you think right now. What is chaos?
Behavior that cannot be predicted easily with linear modeling.
This is kind of close. Can you put some time frames? Like cannot be predicted, and we need a time frame here. In the short term, in the long term, never.
Behavior in the long term cannot be predicted based on the
Okay, yes.
behavior in a specific time.
This is one of the components. It's a necessary but not sufficient component of chaos, but it's true. So we'll look at chaos, what exactly it is. There is a strict definition kind of what chaos is from a mathematical point of view. It's not the same as you see in popular books or movies, butterfly effect and stuff like that. All right. It's stationary, or it's also called equilibrium points. Mind you, we make no statements about the stability of these equilibrium points. We'll investigate how to find that out. But for now, these are equilibrium points. And the number of equilibrium points and their stability depend on the control parameter. Okay? So you can immediately see where we're getting to. By varying the control parameter, u, in this case, or vector of control parameters, we expect something to change with these equilibrium points. And this is the change in the system that we observe, the system behavior that I talked about. Right? Something is going to happen to these equilibrium points. Before that, let me give you a few notions of stability. Even without introducing any mathematical treatment for finding stability, let's look at this point here. If we're at that point, the system is static. It doesn't change anymore. But imagine there is a little shock to our system. So, random shock. And suddenly, we jump here. Whoa. We jump right here, okay? What happens then? What would happen in the next few time periods? We're here, which means that the rate of change is negative, right? This is below the 0, which means that x, so x here, would decrease in the next time period, right? So we will be kind of pushed here, but because of this dynamics, we'll go back to our original position at 0. The same thing, if we're pushed up there, the rate of change is positive, which means